Hello, my dear students. This is the very first class of this Newtonian mechanics course. In this, I am Sheikh Jahiruddin. You already know that. In this class, we'll be discussing dimensional analysis. So, what we'll learn? We'll learn physical quantities and units. What is SI units? What is a dimensional analysis actually means? We'll deriving dimensions of some basic quantities as well as gravitational constant and Planck's constant. We'll tell you the dimensional homogeneity, we'll apply it for some problem, simple pendulum problem, Stokes law problem, and some other problems also. And at the end of the day, I will tell you the Buckingham Pi theorem, and we'll finish this class. So, okay, friends, this is the plan. So, what are physical quantities and units? Actually, in physics, we deal with some quantity. What is it? First, then how much it is. So, we need to have an unit of everything. When we measure length, we need to have an unit. When we measure weight or mass, we need to have an unit. So, they can be quantified. So, these are the quantities which physics mostly deals with. Some other quantities which cannot be quantified, like love, your feelings to someone else. It is not exactly be quantified in physics terms. Of course, it might be quantified in some other theories or in some other subjects, but at least this cannot be quantified in terms of physics or what quantity we means by. So that words, it cannot be quantified, although they are very important. So now we focus whatever relevant to physics only. So some SI units of very common things. The SI unit of time is second. SI unit of length is meter. You know that. SI unit of mass is kilogram. Unit of current is ampere. Unit of temperature is Kelvin. Unit of amount of substance, mole. Unit of luminous intensity is candela. So all these are the fundamental sets of unit. The basic sets of unit are there. So we have here 7 units. In terms of these 7 units, we can express any quantities, the unit of anything in terms of those. Like that is the dimensional analysis. So in terms of all these fundamental units, we'll be expressing everything. So that will be very interesting. Okay. So the first few things about dimensional analysis are the relation between physical quantities do not depend on the system of unit chosen. That means if you choose a CGS unit or SI unit, that does not change relation between the quantities. Like forces, the rate of change of momentum, F is dp dt, that is Newton's law. We'll study it later. That does not depend on whether you are taking your mass at kg or gram. So how much I am there? Okay, little bit shifting. Will do. So of course, the dimension of a physical quantity do not give complete information about it. It cannot give complete information. Dimensional analysis is a tool, but this is not a whole physics. But that is very important tool. By dimensional analysis, we'll get information about how the quantities are related. That is very important, and that have many practical aspects also, many practical applications we did using dimensional analysis in history. You'll know that, I'll tell you. Like many quantities we have, next part, many quantities we have same dimension. You see, work and torque, they are two distinct physical quantities. Nowhere they are proportional or something, but they have same dimension, which is same as energy. So energy, work and torque, they have same dimension, but they are totally different. Dimension of both sides of a physical relation must be same. This is very important. If you're equating two quantities as an equation, left hand side and right hand side, the dimension should be same. That will apply it. Dimension of each quantity in a physical relation must be same. As A equals to B plus C, if I say it, the dimension of A should be equals to dimension of B and dimension of C. Not dimension of A should be equals to dimension of B plus C. This is not. Dimension of each quantity must be same. Dimension of A should be dimension of B should equals to dimension of C. So I think this is a misunderstanding there. So I should insert another equation. Say if A equals to B plus C, then the dimension is like this. That is great. I can write everything, whatever I want, both in tight form or in handwritten form also. Make it a little bit small. As I write it small, make it bold. So that's it. Now I will proceed to dimension of some basic quantities. Dimension of length, mass and time should be denoted as L, M and T. Dimension of current, temperature and mole numbers are denoted as I. Temperature sometimes at K, sometimes at big theta. This is capital Greek big theta. And the mole number is just written as MOL inside a third bracket. So if I derive the dimension of the basic quantities, like velocity is length by time. This is LT minus 1, of course, L by T. Acceleration is length by time square, derivative of velocity. We'll discuss this later on when we read kinetic. That acceleration is LT minus 2 then. The force is, mass into acceleration. So force should be mass into acceleration, m multiplied with LT minus 2. So it will be mLT minus 2. The energy is an integration of force. So the dimension of energy should be the dimension of force into distance. So this should be mL square T minus 2. Just add another L in the force. That will be the dimension of energy. Now we'll proceed to dimension of G and H. As we know, the dimension, the Newton's law of gravitation. Is my recording is on? Yes, this is on. So the dimension of, the Newton's law of gravitation is F equals to G m1 m2 by r square. So the dimension of force on the left hand side should be equals to the dimension of G, dimension of M by dimension of r square. So the dimension of F is, as we already have seen, this is mLT minus 2. So here this dimension of force should be equals to dimension of G multiplied with m square, as there are two m's here, by L square. The distance is L. So G, dimension of G, m square into L to the power minus 2. Hence I get the dimension of G is m to the power minus 1 L cube T to the power minus 2. That's very easy. Now the dimension of Planck's constant. So here there is a relation how the Planck's law was first defined, that energy is quantized in black body radiation, and that relation was h nu. Should I add another word just to just to make it a little bit attractive, that gravitational constant here, Planck's constant there, so that distinct. That is very easy. Just a minute. Sometimes you need to also have a break, so I as a whole make this a little bit down, so I got some space there. That's beautiful, right? Okay, so now come back to our main part. So E was related with H as E equals to H nu. Nu is frequency, so the dimension of energy should be equal to dimension of Planck's constant multiplied by the dimension of frequency. So what is frequency? Frequency is 1 by time, right? If I measure frequency, I tell the frequency is 20 hertz. That means 20 accelerations in second. That is 20 hertz. So 20 oscillations per second. That means your dimension of oscillation should be inverse of your dimension of time. Per second counts. That's why the velocity in velocity, so velocity is 10 meter per second. So in that per second, the dimension becomes 1 by t. So here, I tell you that the dimension of E, which was ml square t minus 2, is equals to the dimension of H and 1 by the dimension of time. So ml square t minus 2 is equals to H by t. Here I get H as ml square t minus 1. As simple as that. This is a very simple. You just put your dimensions and you get that dimension. We will apply it in other problems also, don't worry about it. So we got the dimension of G and H. Now once again I tell you the dimensional homogeneity. I have already told you, but in a refreshing manner, or a formal manner. For a mathematical relation among a number of physical quantities to be a valid relation, the dimension of all the terms occurring in the relation have to be the same. I already told you there. But this is formally, I write it down. One cannot add up physical quantities with different dimension. Like I cannot add 1 kilogram of rice with 1 meter of, say, what? 1 meter of stick. Or I cannot add 5 kilos of potatoes with, say what? With 10 seconds. That it does not make any sense. So we cannot have add up any physical quantities, any two physical quantities with different dimensions. So more generally, it is not possible to add or subtract two terms with dimension unless the dimension may be complicated. The dimension may not be just L, T or M. The dimension could be the dimension of energy, dimension of torque or anything. So in general, if you have a quantity with dimension of L to the power A, M to the power B and T to the power C, and we add with it another term with dimension L to the power X, M to the power Y and T to the power Z, we cannot add or subtract unless the exponents are pairwise same. That means unless A equals to X, B equals to Y and C equals to Z, we cannot add or subtract any two terms. That is the principle of dimensional homogeneity. I think technically you know all this, but okay, this is a little bit of formality. It's also there. So then I proceed to another important theorem like this. Like, just principle of dimensional homogeneity cannot guarantee the validity of the relation under consideration. What is this? That dimensional homogeneity is a necessary condition, but not a sufficient condition to have a relation valid, because in dimensional analysis, we don't know the constants. So what are they? You know, S equals to ut plus half of at square. This is a relation. But say if I say S equals to ut plus 1/3 of at square, this is dimensionally valid. Definitely dimensionally valid. Just give me a second. This 1/3, or but this does not actually comes from dimensional analysis. So this is the real physics law that defines this as S equals to ut plus half of at square. So this will be the correct equation, right? That's it. So that this will be the correct equation. Need to do it a little bit small. This is the correct part. You read it later. Okay. This is correct. So what I'm telling to say is, if an equation is dimensionally valid, that does not mean that the equation is correct. So equation having a dimensionally correct relation is a necessary condition, not a sufficient condition. That should be very clear to you. Both the equation are dimensionally correct, but this is wrong because there is 1/3 there, but this is correct because there is half there. So if you found any equation which is dimensionally correct, you'll say, yes, this may or may not be correct, but this is correct apart from a constant, apart from the constant factors. If you ignore the constant factors, the equation is correct. But as we see in real life application, many times that exact numerical factors is not that important than the dimensional relation. That's why the dimensional analysis becomes more and more important, because many a times what we need to know is just how a quantity varies with L or M or T or the current. So now let's go to some application. You need to pause the video here, or after I explain a bit, then you need to answer it. But the question tells you that three fundamental constants are very much important to physics. One is g, one is h or h bar, whatever, and the third is the velocity of light. We have already derived the dimensional exact relation of g and h, and c is the velocity. So this dimension can be determined from here, and a suitable combination of g, h and c can give you the length, mass and time. They are called Planck's length, Planck's mass, or Planck's time. So now, using dimensional analysis, find the following quantity which correctly gives you the Planck length. That means sum of it among these four will have the dimension of length. You may pause here. If you are unable to do, then go back and watch the dimension of g and h, which we have already done it. And then frequency, I have already told you that number of vibration is 1/t. So if you need it, you may use it. So now just try to answer it. Which among this will be dimension of length? Then you try to find out a combination of g, h and c, which will be the dimension of mass or dimension of time. If you have already paused and checked and tried, I would like to tell you the answer will be D part. This will be the answer. I think you got it right. If you didn't, then once again go here and check the dimension of G and H, and then combine it, check it one by one, that which will be the dimension of length. Anyways, so these kind of questions which come to exam. Next, I'll do some examples. There is a simple pendulum. What will be its frequency of oscillation? It can be derived from dimensional analysis apart from that exact constant factor. So the problem is very simple. A mass hangs from a massless spring of length L and swings back and forth in the plane of the paper. The acceleration due to gravity is g. So what can be said about the frequency of oscillation? That means how the frequency of oscillation is related with the possible variables, which is one is mass, its length, and g will be an important factor. So combining this, we need to find a frequency of oscillation, or something with dimension of frequency, that is 1 by t. So the mass of m is m, L is L, and g is L t to the power minus 2, as g is an acceleration. So we take the frequency of oscillation to be related as with some unknown parameters a, b, and c. So the dimension of frequency should match the dimension of the right hand side, which can be found from m to the power a, L to the power b, and g to the power c. So as you see, the dimension of frequency is 1 by t. So we make this left hand side as 1 by t, and right hand side as m to the power a, L to the power b, and L by t squared to the power c. Then I equate it one by one. The t to the power minus 1 is m to the power a, L to the power b plus c, and t to the power minus c. Sorry, minus 2c. So then what can you say about it? So what can you say from it? You'll see that minus 2c will be minus 1. That means 2c is 1. This is the first thing you observe. And there is no m and no L in left hand side. So a should be 0 and b plus c should be 0. No m, no L at LHS. So minus 2c is minus 1, b plus c is 0, and a is 0. That gives you a is 0, c is minus half. Then, the c should be, just a minute. I got it a little bit wrong, I guess. Minus 2c is minus 1, so c should be half. So I got it wrong. I'm very sorry about it. C is B is minus half, A is 0. So hence the frequency, actually I got it wrong for time period. G by L. That is the frequency. I mistakenly wrote the time period here, so that's why I got that wrong. This c is not this c, so I should be very careful writing the constants. So I will write k is a dimension as constant. So within that k factor, I don't know k here, but I can understand that the frequency of oscillation should vary as square root of g by L. So if I don't know even k, I can find the ratio of nu1 and nu2 if I know the L. If I know the length, that means the nu1 by nu2 should be square root of L2 by L1. That sometimes become very important in practical applications. So as we see, your time period will be here, let's say 1 by k because time period is 1 by frequency. That is very familiar equation. You know that time period is what? 2 pi root over L by Z from your basic physics knowledge. You may not know it, but don't worry. And the time period of a pendulum is 2 pi root over square root of L by G. So this thing we can do. These are the some examples what we can do with dimensional analysis. So you'll see lots of examples later on. I'll give you an assignment which deals with some problems of dimensional analysis. So okay, if we are having any doubt, just pause it, replay it, and see what is going on there. So time period is 1 by. So if you don't know it, sorry, yes. Okay, so now we'll go another very important application of dimension analysis. So to do that, first we found the dimension of eta. Eta is viscous constant, the constant of viscosity, just tell. So viscous force per unit area is defined as F by A is eta. This dV dx is called velocity gradient. That means how your velocity changes with respect to x, with respect to distance. This is viscosity. We'll discuss the phenomenon of viscosity later on. But if I just tell you that there is something called viscous force, the relation of viscous force with velocity gradient is F by A is eta dV dx. V is velocity and x is displacement. Then you can easily find the dimension of eta from here. That would be very simple. Velocity gradient is nothing but like this. If I just draw a diagram, if your liquid is flowing like this, so your distance from, if this is right at x, v is not a constant there, v is a function of x. So that's why this dv dx comes. This is called velocity gradient. So okay, now I write the dimension of f here, mlt minus 2 by L square. L square is from this area, equals to the dimension of eta dv dx. So that v is lt minus 1, the dimension of v, and the dimension of x. Whenever we have derivative, we just write the dimension of the quantities which is being derived, being derivative to. So this is lt minus 1, this is L. So we just equate this and we get the dimension of eta as ml minus 1 t minus 1. This will be important. This will be important in our future problems. Okay, next I go to the Stokes law. What is Stokes law? So what is the physical condition here? A spherical body of radius r moving with a velocity v through a fluid whose coefficient of viscosity is eta. What should be the resistive force due to viscosity of the fluid? This could be a real life problem, and this you may encounter it anytime. That I have a mass there, the mass is falling, this is a liquid. So as we see, the resistive force could be function of many possible things. So what we see there, I got this thing, I think this should be copied in every slide because it was not a pre-made. So, okay. So the velocity of this particle when going down inside a liquid can be a function of the particle radius, of course, the velocity itself. I'm trying to find the resistive force, right? So the force could be function of r, radius of the particle, velocity v of the particle. Eta is the characteristics of fluid, that how much force fluid itself depart on. The eta is an estimation of that. So, and will be that form, increase a bit. So if I equate my force with this dimensionally, that force should be some constant k with r to the power a, eta to the power b, and v to the power c. I assume that force is a function of only these three quantities and not of any other else. If you can imagine if something else should be there, you may think about it, that how much force will be departed on this particle may be function of some other parameters. If you think about it, you may try about it. But I initially takes only r, v, and eta as a dependent variable of that force. In many unknown problems in physics, we start with this, that let's say this may depend on this, and this variable only. Now take a dimensional analysis and do it. So, okay, we do it and see, check how this force depends on r, eta, and v. I write the dimension of force here, mlt minus 2. That should be equals to L to the power a. Where the L comes? This L comes from the dimension of r. R is the radius of the particle. The dimension of that is L. Where from eta comes? I derive the dimension of eta here. Eta is ml minus 1, t minus 1. So I write the dimension. Sorry, so here I write the dimension of eta as eta is ml minus 1, t minus 1. All will have to the power b here, m to the power b, l to the power minus v, t to the power minus c. So I remind it that dimension of eta is m l to the power minus 1, t to the power minus 1. And then the velocity. Velocity is, of course, L t minus 1. So I just use this here, the dimensions. So if I just equate it with this, what I get? I will take m's power in one place, L's power in one place, and the power of t in one place. So I see this. This should be equals to what? I should have wrote another line. I write it now. You can think with me that this is m to the power, m has only appeared once, L has appears 3 times. Sorry, I don't know what happened. So L had appeared 3 times, which is a minus b, c. Then I have t appeared 2 times, which is minus b minus c. That's it. I give a equal sign there. I make it a little bit large. Okay, so then I equate the power of m here. Here left hand side the power is 1, right hand side power is 1, so a is 1. Sorry, I wrote it wrong. M has b there. Very sorry about it. So your b is 1. Compare the power of L. Left hand side the power of L is 1. So here the power is a minus b plus c. So that means a minus b plus c is 1. T is minus 2 here as a power. Here it's minus b minus c. That means b plus c is 2. And if you just solve it, the three linear equations, you get a equals to b equals to c equals to 1. As simple as that. So that means your force will depend on k is a constant, but other three quantities direct linearly. F is proportional to directly with the radius of the particle. If the radius of particle increases, F increases direct linearly. If your eta increases, F increases direct linearly. If your V increases, F increases direct linearly. That means, if I say another more explicitly, that if you're comparing a force, say F1 by F2, that K is same everywhere, so that K cuts. So this will be R1 1 E1. Then I copy it and change it to 2. Then, that's what I wanted. See, writing equation in PowerPoint is not that tough. They have improved a lot. So it directly works with LaTeX right now. It's I'm just using LaTeX symbols here. So that means this. So you know this. It's very easy. That's so easy that you don't need to fear anything about it. So okay, now once again I give you an exercise. Just pause the video and think about it. And this actually used previously. Sometimes it's false. This problem is mother of all dimensional analysis. Historically, this analysis was used before the atom bomb was actually tested. So it is a following nuclear explosion, a shock wave propagates radially outwards. If E is the energy released in the explosion and rho is the mass density of the air, so we ignored the temperature of the ambient air. So I need, using dimensional analysis, I need to find how the dimension, how the radius will depend on E, rho, and T. And this question appeared in CSI NET exam also. And it was very important to know before the atom bomb testing that R will be the radius of the shock wave front. Shock front, that means shock wave front. So how much, how long this impact of the atom bomb will go on. I may form a different language. I may form this function, this question in a different language, but still this is exact what appeared in CSI NET. So what happens is I need to find the radius R, how this radius R, what is radius R? The impact. Doom, a bomb blasting, how much the impact will spread. Let's call this as radius of the shock wave front. and then how it depends on energy, rho, and time t. So energy released can be previously estimated, rho is the mass density of the air, and how much time it will take. If you simply pause here and try to answer that question, it will be very easy. Try it. Pause, try. I think you got it right. The answer should be A. So this is a real life problem. I can reframe this problem in a different manner, like this. So the same problem actually, the statement is a little bit different, so that your understanding becomes better. That we need to estimate the yield of the fast atomic bomb blast. Such a blast which creates shock waves of air. You know that, I already told you. Which creates a radius r at a time t after the blast. The air density is rho, and we want to estimate the blast energy E. So here I give you the data so that you got this problem more interesting. So the photographs of the blast indicate that when r is 100 meter, at the time of t is 15 millisecond, the density of air is this. So you need to estimate the blast energy, a rough estimate, within a constant factor. I don't know the constant factor. So, but still I can have a relation, dimensional relation, and can have some estimate of that. And then how much mass energy was used in this blast. So make a pause of that video right now. Study the solution what I provided you. This is very simple. If your E is this, the relation of energy with radius rho and t is this. You already did it. And if you put the numbers, you can have an estimate, a huge estimate. That was done initially, of course. And then mass energy equivalence, you can get a very small fraction of mass was converted into energy. That much energy is equivalent to near about 0.5 gram. Okay, so we need to sum everything up quickly. Now I go to Buckingham's Pi theorem. This is a very interesting theorem. It has a huge application, but you don't need to go to very large detail of that. Just see that statement, which is, if all the parameters and variables, including the dimensional constant relevant to the solution of a physical problem, are known, if all the parameters are known, then it can be formulated in relatively simple terms by introducing an appropriate set of dimensionless parameters and variables before attempting a solution. You should tell, yes, sir, this is very obvious. Isn't we are doing the same thing from the last half an hour? Yes, we are doing the same thing from last half an hour. But this is a theorem which can be formally proved. So the thing is, if all the parameters and variables are known, if I know a quantity depends on which part, like this, it depends, the energy released depends on air density, radius, and time. If I know this, I know these three parameters. If I know that radius depends on E, T, and rho only, if I know this, if I know the force on a liquid, on a viscous liquid, depends on the particle's radius, eta, and its velocity, then it can be formulated in relatively simple terms by introducing an appropriate set of dimensionless parameters and variables before actually attempting a solution. So that is a formal acknowledgement of what we are doing. Of course, it has some other applications also. Some complicated problems can be simplified in using dimensional analysis, but that is a different story. You don't need to go. You should be you should be limiting yourself what I am telling you. And that's why I am your guide. Okay, so just know that statement and understand that we were using this. We assume this to be true. Yes, if I know the variables, I can find a dimensional. I can find a relation of known and unknown quantities using the dimensional analysis. That's it. If some of the variables relevant to a problem are not known, then the efficiency of the principle of similarity is greatly reduced. That's okay. If I don't know something, if I miss a variable, that okay, I assume that this depend on this, and this. If I miss something, of course, the efficiency of dimensional analysis will reduce. And that will lead to an incomplete formulation in terms of dimensionless variables. Surely, it will do that. So, that's it. For exam purpose, in BSc theory courses, we may not expect questions from here. It is not explicitly mentioned in the general syllabus. As if your university do mention it, then of course question may come. But it is very important dimensional analysis in competitive exam. Question asked in IIT JAM, CSI, NET, GRE physics, and all kind of exam. On an average, one question in every JAM is related with dimensional analysis. One question is in every CSI and NET is directly from dimensional analysis, or sometimes it is hidden, but you need to apply in dimensional analysis. As you will see, if you have 4 options and the dimension of all 4 options are different, then you can easily find the answer by using the dimensional analysis and equating the dimension of the options with the quantity asked. So as we discuss later on, we'll come across this type of problems. In interview, of course, dimensional analysis, you may be asked to derive something using dimensional analysis. You may be asked to find something using dimensional analysis. So with this, I sum up this dimensional analysis class. You do assignment 1, posted in Google form in the course page. Do quiz 1, which is posted in the course page in the form of interactive quiz. I will try to make more interactive quizzes. And of course, assignments are ready in terms of Google form. And if you are watching this lecture till now, you can enroll the complete course here in this link. This link will be given in the video description, whatever, if the video is posted in Facebook or YouTube, the link will be there. You will get lecture videos, PDF files, notes, assignment, tests, WhatsApp groups, doubt clearance, everything if you enroll this. The course fee is not 2,000. You are getting a discounted price of ₹999, as I am first time launching this course. Slowly, as we progress in next time, as we learn multiple times, the course fee will of course be increased. Okay, but right now you have the opportunity to grab this course as $19.99. So I am there. So you're watching me and this course. Next class will be discuss some basic mathematics, which is vectors, differentiation, and integration, all these things. So finally, you can contact me anytime here. Our email, Facebook page, Facebook group, YouTube links, all are there. Thank you so much for your kind attention.